Hi guys, today we're going to cover a question that I got from somebody on YouTube, and so we're going to have a little physics science lesson to answer this person's question tonight or today. So let's have a look at this question. So what we're going to end up doing is a comparison of real climate physics versus fake climate change alarmist physics, which is just pseudoscience in fact. So let's have a look at this fellow's question from Rhino on Ingo, whatever that means. Your argument regarding the phony expansion of the amount of Earth's surface that is or could be heated by the sun at any given time makes sense, and I was unaware that the models that are based on it are starting from a false foundation. Yes, indeed. Thank you for comprehending so far. Many people can't that are inside academia. That is, however, apparently one of your key points, to share this revelation with as many people as possible so that they can better understand the story being told by the anthropogenic climate change true believers and opportunists. Indeed, should spread this far and wide. It's very easy to understand, and it's the greatest fraud that has ever occurred in scientific history. It is a massive, massive fraud of the greatest scale possibly imaginable for where it occurred and what the subject matter is about. I'm not yet tracking the nuances of why the equivalent temperature for heating in the fictitious greenhouse effect is minus 18 degrees Celsius. Is that related to the idea that they are claiming that the sun is directly heating the air? If you or one of the others could elaborate on that point, it would be helpful to me. Okay, so we will cover that minus 18C question. And we'll have our little science lesson now, okay? So we answer that question by starting in astrophysics and quantum mechanics. So all that we can measure from a star is its light. But from its light, what can we tell or infer about the actual physical nature of a star? We've been able to see starlight for thousands of years. And starlight has been falling on the earth for longer than that. But as far as people looking at starlight, we've been able to see starlight for quite a long time, and we can tell that some stars are brighter than others, but we would like to understand why. What is the physical difference between stars that makes them different? So we can measure the star's brightness, or its luminosity, as we call it in astronomy. But by passing the light through a spectrograph, we can also measure the light spectrum. So that's when you break the light up into its constituent frequencies, as through a prism, like you see with a rainbow during a rainstorm or after a rainstorm. And so this is the spectrum of sunlight. So someone has nicely shaded in here where the visible region is. So you have red, and then deeper or a longer wavelength is invisible. So he's just colored it in black. I really like this diagram here. And then of course the opposite way is violet and then ultraviolet. So that's the sun spectrum. Very, very interesting. That's a very, very interesting thing that we were able to start measuring about 150, 200 years ago. Was the spectra of starlight. It was very interesting to start being able to do this. At around the same time, we in science were trying to develop the physics and the mathematical formulae for how an object would thermally emit radiation. How it would emit radiation from, say, a glowing hot object. How does a glowing hot object emit radiation? And many, many years were spent on this problem, and many scientists worked on it, and the math was always never working out, and they were running into what was called catastrophes, ultraviolet catastrophes, just meaning that there were infinities in the equations that they were trying to develop. But then Planck hypothesized that perhaps energy is quantized. Perhaps energy isn't totally continuous, but is discrete and is emitted in small packets of energy, which he called quanta. So basically the difference here is similar to that between analog and digital in a sense, right? In analog, you have a continuous sweep through values, for example, but with digital, you have steps between values, right? So it's kind of like that. So he hypothesized that perhaps pure energy, such as light, thermal electromagnetic radiation, is emitted in discrete packets or discrete quantities, which he simply called quanta, right? And that's where we get now quantum mechanics from. So really what quantum mechanics means is the mathematics, the physics, or the mechanics of how energy behaves when it is emitted as quanta. That's what quantum mechanics means. It basically means the mathematics of energy when energy is quantized. How does that mathematics work out? So Planck derived this spectrum, this formula, which governs how it doesn't govern, which says how light is emitted thermally by a hot object. And it has been found that stars emit, for example, this stellar spectrum from our own sun, emit very similarly to black bodies, to perfect thermal emitters, which is what Planck's equation is about. And the Planck's law, so this is called Planck's law. And so Planck's law has a whole bunch of constants of physics in it. So H is Planck's constant, C is the speed of light. So this lambda gives you the function of wavelength, but deep inside here is the temperature. So this function basically changes its peak, transfers to higher frequency for higher T, higher temperature, and it grows. Okay, so basically this curve just grows this way and becomes bigger and bigger at higher temperature, and at lower temperature basically this peak extends over into the infrared. So that's how you get the difference in color. So our star, the sun, is yellowish because it peaks around this region, but hotter stars peak in the blue, and so they appear blue, and cooler stars might peak in the red, and so they will appear red. But one thing that is then really interesting is that, well, given that you have the spectrum of a star, can you not then estimate what the temperature of the star is? And so you can do that basically, I mean, you can sort of think of it as a best fit. But what we really go to is the Stefan-Boltzmann law. So what the Stefan-Boltzmann law does is it just integrates the entire ideal curve, the ideal equation here. It integrates the whole thing and says the whole flux that you get under the entire curve is equal to a very simple expression as found mathematically when you work this out, as you do in a physics classroom during your education. So the whole area, the entire energy under the curve, under the black curve, the ideal one, which is this equation, is simply equal to a constant times the temperature that's inside this equation, but to the fourth power. So that's an extremely simple equation. So this temperature here is then called the effective temperature when this equation is applied to an actual spectrum. So given the total area or energy of the star's spectrum, what would be the equivalent temperature if the star emitted all of this energy in the star's actual spectrum, but perfectly as per Planck's formula? So what if you take all this energy of the actual spectrum from a star and call that the F? What is the equivalent T then that you would need for that F? And as you can see here, it's not a perfect fit, but it's, you know, sort of the best fit, right? It's sort of the best estimate. So this is called the effective temperature. In astronomy and physics, this is what we call the effective temperature. It's if this star was emitting perfectly, for example, this spectrum of our sun, if this sun was emitting perfectly, like this equation, if it was emitting perfectly, thermally perfectly, then it would have a corresponding temperature, which we call the effective temperature, and for the sun it works out to about 5,778 Kelvin. Okay, so we still use this Planck curve approximation, or this Stefan-Boltzmann law approximation for effective temperature, even for stars which have not so nice spectra. We still just use it because there's no way you can actually measure a star's temperature, can you? First of all, if a star is like our sun, they're gaseous, right? So at what depth in the atmosphere are you going to measure its temperature? Because the temperature changes with depth. It gets hotter and hotter as you go deeper into the star. So there's no real position to say this is the position at which the star's temperature is a star's temperature. There's no such thing as that, right? All stars like our sun and all other stars have a temperature that changes with depth. But if you want to give the star something like, you know, an effective temperature, right? An average temperature is something that you can treat as a basic temperature of the star. Then you use this effective temperature. So it's basically a fictional temperature. It's not real. It's just saying if the star emitted perfectly as a flat surface or as a surface, as a solid surface, then it would have this temperature. Okay, so it's just an effective temperature. That's why we call it effective. Okay, so we can apply this Planck's law and the Stefan-Boltzmann law to get the effective temperature then for the Earth using the same sort of idea. And we just do that by applying the law of conservation of energy. So the basic idea there is that the only energy that the Earth has to emit is the energy that it receives from the sun. And of course, we assume that geothermal energy is a negligible contribution because that's been measured as such. And so basically, after billions of years of the Earth being around the sun, there should be some sort of basic energetic equilibrium between the energy that the Earth receives from the sun and the energy that the Earth emits. Basically, the Earth has to be emitting the same amount of energy that it actually receives and absorbs from the sun. So that's just conservation of energy, right? So this doesn't assume that the Earth is in thermal or thermodynamic equilibrium, especially the atmosphere, because certainly the atmosphere is nowhere near thermodynamic equilibrium, nowhere near. But in aggregate, in average, the energy coming in should equal the energy coming out, and so we simply apply the law of conservation of energy on its own. So here is then, for example, the spectrum of the Earth's output. And so when you apply Stefan-Boltzmann law for the entire area, which is the total energy under the Earth's spectrum, you get 240 watts per meter squared approximately, which gives about 255 Kelvin or minus 18 degrees Celsius. So the effective temperature of the Earth is then minus 18 degrees Celsius. Okay? So what this what this energy is then, is the high intensity solar heating, which has come in and created the climate, then leaving as lower intensity energy. Between the input and the output, the solar heat creates the climate. The climate is solar heat transfer through the Earth and through the atmosphere. And then the atmosphere and the constituents of the atmosphere, such as water vapor and everything else in there, dissipates the solar heat and spreads it around. Okay, so this effective temperature of minus 18 degrees Celsius, or 240 watts per meter squared output, which is the aggregate average from the entire surface area of the Earth at once, that is exactly what is seen from space. That is indeed the average output of the Earth as seen from space when measured by satellite, and there is no discrepancy and no problem with that. So indeed, the effective temperature as measured by the average output of the Earth is indeed minus 18 degrees Celsius. That is indeed the effective temperature of the Earth. And the Earth emits on average 240 watts per meter squared outward from its surface. No problem with all that. The problem comes in when this output is used as a solar input. How can any temperatures, because then as they do in climate alarm. So in climate alarm, the problem comes in when this output effective temperature of minus 18 degrees Celsius is used as a global solar input over the entire surface area of the Earth at once. Because then they stump themselves with the question, how can any temperatures be above minus 18 degrees Celsius if the solar input to the Earth is minus 18 degrees Celsius? But of course, they've committed their first mistake. Minus 18 degrees Celsius is only the effective temperature of the Earth, and it's the output of the Earth. It has nothing to do with the input or the heat or temperature generating power of incoming sunlight. Nothing. But they reverse it, and that's what they do, and they create this problem for themselves. So, before we complete that analysis for what they do wrong, let's first complete the proper rational analysis. So to complete the proper rational Earth analysis with real physics, we simply stay consistent with the meaning of what our averages are and continue on with the minus 18C, that if it is to be a real average temperature you can measure somewhere, then it should correspond to the average atmosphere, as we do in astronomy. As I said, for a star, the temperature of a star actually changes as a function of its depth. There is no single temperature of a star, just like there is no single temperature of the Earth. But for a star, the effective temperature is generally found within the range somewhere in the depth of the atmosphere from which the star is emitting light. So you would expect something similar for the Earth, or you should treat it the same way as for the Earth. So let's treat this minus 18C as an aggregate average temperature that you should find somewhere in the average atmosphere. In that case, you look at the average atmosphere, right? Because we're looking at this aggregate output, which is the effective temperature of the Earth, as some sort of as an average output of the Earth. So in that case, to stay consistent with averages, you must find where this minus 18 degrees Celsius occurs. And you would, of course, expect that it occurs somewhere within the average of the atmosphere. And so where it actually occurs in the atmosphere is at about 5 to 6 kilometers altitude. Okay, so with that, we also have the existence of the lapse rate in the atmosphere. Now, this lapse rate is caused by convection and gravity. It's called the adiabatic lapse rate. And this you can easily derive. I'm not going to show it now, but it's extremely simple to derive this equation. You can derive the lapse rate equation with high school level physics, with basic introductory physics knowledge, similar to Newton's laws of motion and things like that, high school students learn in high school. They can derive this equation. There are also much more complicated ways to derive this equation, much more advanced ways to calculate this equation, or to derive something similar to this equation using thermodynamics, but it ends up coming out to the exact same value, or to the exact same sort of pattern. So that kind of is cool, that you can use really, really simple physics and really, really complicated physics and still get the same result, that you have this adiabatic lapse rate that must exist in the atmosphere. So if we simply apply this equation of the lapse rate, given that there's an anchoring of the average, right? So the minus 18 degrees Celsius is now going to be anchored as an average, or thought of as an average temperature. And we're going to anchor that to where it occurs, to where it actually occurs. And that's going to be the anchor in the atmosphere's depth, or height above the surface, actually, I should say, which is around 5 to 6. So that H naught here, that's the reference height, which is 5 kilometers. And then T naught is your reference temperature, which is minus 18 degrees Celsius. So if we want to find the temperature at the surface, so the temperature at a height of 0 above the surface, so temperature at the surface, so T of 0 for T of H here, then becomes this value, and this is what this minus G over Cp is. This is the value that you can derive with either a very simple equation from high school physics or extremely advanced physics from thermodynamics. You get the same value. So you have minus 6.5 Kelvin kilometers times 0, because that's where you want to know the temperature, minus 5 kilometers, which is the reference, and then plus your minus 18 degrees Celsius, which is your reference temperature. And the result of that is here it is, 14.5 degrees Celsius, and the accepted average, measured average surface temperature, is around 15 degrees Celsius. So you can see, with some very simple analysis here, we have come up with an extremely accurate and extremely precise measure for the average temperature near the surface of the Earth, of the air near the surface of the Earth, near the surface. That's an amazing result. Really great. All done. We understand the atmosphere. We understand the average atmosphere now. It's all finished. But let's go back to the fake physics of political climate physics. It doesn't understand the meaning or logically consistent use of averages. So it thinks, political climate physics thinks, that the average output of the effective temperature of minus 18 degrees Celsius for the Earth can be used as a global freezing cold solar input on a flat Earth with no day and night. Now, of course, why would you do that? You can't do that, and it should be readily understood as being absurd to do that. Why would you treat solar input as being spread all over the entire surface area of the Earth at once, where the Earth is flat? where the solar heating power is only minus 18 degrees Celsius and cannot generate any higher temperatures than minus 18 degrees Celsius. That's a very strange thing to do, isn't it? And that's because they're reversing the output for the input. They're not understanding how to apply these averages and how to use them. So then it goes on to think that the climate must therefore create itself by providing for itself twice the energy than the sun provides, hijacking the name greenhouse and basically making the sun irrelevant. And you see that from this diagram here, which is a publication in a meteorology journal by some climatologists. And here they show that the sun is only providing this value in watts per meter squared, 168, but the atmosphere is providing for itself pretty much twice that value out of nowhere. Of course, sunshine has an explanation for where it comes from. It comes from fusion power inside the sun. That's where that energy comes from. There's no energy being liberated in the atmosphere. There's no combustion going on. There's no fusion going on, fission, anything like that. The atmosphere is basically inert. Yet, they assign that the atmosphere must produce basically 2 times the energy than the sun so that the climate can create itself, because they've treated the sun as basically being entirely irrelevant to the climate, because the sun, they think, cannot produce any heating or any temperatures or any physical responses higher than what you find at minus 18 degrees Celsius, higher than minus 18 degrees Celsius. Amazing. So because the climate creates itself, yeah, this is the really funny part, based on the above. So guys, because the climate creates itself, you should feel bad and guilty about it, and you should be taxed for it, and you should accept unlimited climate refugees for it. Brilliant, right? I mean, who came up with this ridiculous idea? It's so stupid. It also ignores entirely the existence of the lapse rate. So the lapse rate is like the most important thing about the atmosphere. If you have any knowledge about how the atmosphere changes with altitude, if you climbed a mountain or you just have basic knowledge about things, you know that the atmosphere cools with altitude. The climate physics scenario and what they've derived completely ignores the lapse rate. They don't include it in their diagrams at all. They're just trying to say that it's all this fake greenhouse effect creating the physics and creating the climate. So let's look at a tree diagram comparison. So we start with the calculation of the effective temperature of the Earth. Well, that's all fine. That is what the effective temperature of the Earth is, and the effective temperature of the Earth is minus 18 degrees Celsius. That's all fine. So in real climate physics, you use that effective temperature as the Earth's output, because that's exactly what it means, and that's why and how it was derived. What fake climate political physics does is use that effective temperature as a global solar input on a flat Earth with no day and night spread over the entire surface area of the Earth at once. In real climate physics, we treat that effective temperature as an average. So you should find it somewhere around the average of the atmosphere. In fake climate political physics, they treat that effective temperature as if it should be the warmest possible temperature that you should be able to find, because that's all that the sun is providing in their mind. So in real climate physics, we can incorporate the adiabatic lapse rate to our analysis of averages and average values. In fake climate political physics, they entirely ignore the existence of the lapse rate, and they don't refer to it at all in their diagram of what the average atmosphere looks like. They entirely replace it with this other model idea where the climate creates itself. So in real climate physics, being consistent with our understanding and meaning of what averages are and how to apply them and where to use them, we come up with a very simple way to quite accurately determine the average surface temperature of the Earth. Very simply, high school students can do it. In fake climate physics, however, they cannot determine the average surface temperature without this falsely named and invented greenhouse effect, where the climate creates itself to make up for what they think is the sun not being able to explain any temperatures or climate phenomenon above minus 18 degrees Celsius. In real climate physics, we can incorporate the daily solar heating cycle. We acknowledge that the daily solar heating cycle is occurring all the time, and that the sun is heating things to very high temperatures and has tremendous heating potential, incoming sunlight. That is what creates the climate. But in fake climate political physics, they have to entirely ignore the daily solar heating cycle, because in their mind, the sun can only provide minus 18 degrees Celsius worth of heating. And so they have to entirely ignore that this sunshine in real time actually carries with it tremendous heat and heats up the surface to very high, very warm temperatures indeed. So that's a tree diagram comparison for you right there. Basically, what climate physics is flat earth theory developed as physics. Guys, look, that's what it is. Look at this flat line. That flat line is a flat plane for the earth. That's flat earth theory. That is precisely what it is. Look, it's a diagram right there. That's a flat earth. That's a flat earth with sunshine spread over the entire surface at once, incoming. So fake climate political physics is actually literally the concept of a flat earth, but developed into physics. That's what it is. And then it's found at academia and taught at our universities. And it's the basis of climate alarm. Okay, so let's look at a couple of responses. I just want to discuss how strange this is. Let's look at a couple of responses that I've been getting for the videos I've been producing here. So one person says, I enjoyed this, but in my view, it's just sort of nonsense. You're doing what all my AGW denier friends do. Oh, there's that term. Yes, I'm a denier, hey? Which is present an argument based on misrepresentations and oversimplifications. I did not draw the flat earth diagrams that are the basis of climate physics. I'm showing the direct references. I didn't make them up. I'm showing them directly from the textbooks and from the university course pages and everything. I didn't make them up. I am showing precisely what they are and what you are doing in them and what they are doing in them. Just one example, dividing the solar constant by 4 is not flat Earth. It's a way of counting the average energy flux over the sphere, which has exactly 4 times the surface area of the cross-section of the Earth. It gives the correct average energy flux. And then look at Roy Spencer just a few days ago in an email to me. I think anyone who claims that the area of a sphere isn't 4 times the area of a circle needs to go back to geometry class. Guys, aren't these the strangest things for people to be replying to me? Aren't those the strange? What do these statements have to do with what I've been presenting to you in my videos? What do they have to do with what I've been presenting you? My problem isn't that I don't understand that a disk area is 4 pi r squared, or is pi r squared, and that a sphere area is 4 pi r squared. I understand that. What I am pointing out is that you cannot take that cross-section disk input of pi r squared and dilute it over the entire surface area of the Earth at once of 4 pi r squared and call that the input, the solar input to the Earth. That's not a meaningful average. Modern academic university political physics does not seem to comprehend what averages are and how to use them. These are the most bizarre responses that I could imagine to my videos. These are from physicists. Roy Spencer is a PhD in meteorology. This Anon fellow is a PhD in physics. You got fellows have been watching, I'm talking to my regular audience, you've been watching my videos that I've been producing, right? Am I talking about that I disagree about what the area of a disk is and what the area of a sphere is? Is that where my difficulty is? These people, these physicists here, these academics, don't seem to be able to understand the most basic things. They're not, it's the strangest thing about it. It's like they're not there. They're just not there as people or something in their minds. They're not there. All right, so that's it for this video. I hope that was educational enough, and I hope I covered the points well enough, and take care.